The computer audio, start video, recording. There we go. That looks pretty good. Yeah. I don't think we have a single student yet. Nope, nobody. Pretty lonesome here. Yeah, but we have 7 minutes before class. I guess I could write up there coming attractions. Homework number 12 is due Thursday. Okay, let me write that down. Homework number 12. And what that is 13104. On page 162, and it's due Thursday. You know what that is? I think that's October 1st. Yeah. Calendar says that's October 1st. How about that? Yeah, there's some homework there. There's some other homework due Saturday, number 12. We could write that down. That won't hurt anything. No, wait a minute. Well, that can't be number 12. That must be number 13, huh? Yeah, let me double check that. I bet that's number 13. Number Okay, and next up your homework number 12. Yeah, homework number 13. Yeah, that'd be number 13. That's problem F14-2. Page 194. And 14-1. Page 195. And that's due Saturday, I believe. So what would Saturday be? 5th, you suppose? No. The 3rd. Of October. How about that? So there's some homework. Hey, we've got Ashley with us. Good going. I'm not alone anymore. And we have Megan, Taylor, Nicholas. Hey, Megan, did you get my email?
I don't know if I did or didn't. I haven't looked at it.
Well, look at it, email me back, and we'll figure out something. Do not change your major. I think, Megan, I don't think there's an issue in this class, but you're in two classes of mine, aren't you, Megan? Or it's calling Megan.
No, I'm only in your class for dynamics this semester.
Oh, okay. Well, I'm mixed up. Maybe that's my problem. Never mind what I just said, Megan. You're okay. Everything is just fine. It's another Megan, I think. Okay. Well, we have a couple of minutes before class starts, and there's a test in your futures. I was looking when that is, but it's way, way far away. It's not till
Dexter.
it's the 17th. And what did you say? I didn't quite hear you.
I forgot to mute my mic.
You've got to meet your maker. Is that what you said?
Forgot to mute my microphone.
Oh, you forgot to mute your mic. That's fine. No problem. That's a long time from now. I wouldn't worry about it. But see, it's on chapters 13, 14, and 15. We're going to try to get into chapter 14 today, for sure. We've been in 13, but I'm not quite ready to leave. We probably should make sure we understand 13. But hey, class is going to start here in about 30 seconds. Does anyone have any comments or questions before we begin our exciting morning together? I hear nothing. Kind of like Sergeant Schultz said, I know nothing. What show was that? What show
I'm gonna
was
guess. I'll guess MASH.
No, it was not MASH. I'll do it again. It's Sergeant Schultz, and he says, I know nothing.
Hogan's Heroes.
Yeah, it's Hogan's Heroes. Good for you out there. Yeah. I'm surprised that you have time to watch anything because you're busy doing your homework. Okay, well, you can read all this on the blackboard there. Here's your last chance to ask me any question. Otherwise, I'm going to do what I want to do. So here's your chance.
Is that exam 2 on September 17th or October 17th?
Thank you point goes right there. It's October. It's not September. It can't be September. Now, who was that?
Taylor.
Taylor. Thank you, Taylor. Yeah, I wouldn't worry about it. It's not even October yet. Not till this Thursday. Okay, well, let's finish up this chapter 13. I wanted to do a review problem 13.3. I'm going to erase all this so we can have the room here. It's in your schedule and your blackboard. But this is a review problem 13.3. And let me find it here. It's a review problem. Okay, 13.3. Might help me find it here. Having a little trouble. Oh, it's a review problem. So it'd probably be at the end of the chapter, do you think, maybe? I can't find it. Yeah, there it is. Review problem 13.3. In my book, it's on page 176. And they have these two blocks there. One of them's 50 pounds. Pretty big block there. I don't know what it's made out of. It looks like it's concrete, like a concrete block, huh? And then they have a smaller block, 20-pound block. This one's 20 pounds, but the big one's 50 pounds, right? Yeah. No, just a minute. Yeah, it's 50 pounds. And see, it's on a smooth surface. Smooth. But see, the surface between A and B, this is A, and this is B. This surface is not smooth. It's got a static coefficient of friction of 0.4 and a kinetic coefficient of friction of 0.3. And then they put a force on block A of 50 pounds. Okay, I like that in red. So here we go. We're going to put a red force right here of 50 pounds. There you go. Hey, you know, we're dealing in English here. We're dealing in the American customary system of units. So that makes it difficult, but we can do it. What do they want to know? Find the acceleration of each block. Okay, well, see, there's some friction between these two blocks, but I don't know whether it's kinetic friction or static friction. We're going to have to think about that. See, the way the equations work is static friction is less than or equal to the static coefficient times the normal, and the kinetic coefficient of friction is equal to the kinetic coefficient times the normal. Well, let's get the normal. Let's put those in red. Now, see, there'll be there's going to be a weight. There's a weight here of 20 pounds. 20 pounds, there we go. 20 pounds. But there's also a weight here, 50 pounds. 50 pounds. And then see, there will be a normal here of 70 pounds. So there you have it. There's all the forces that are acting on the two bodies together. Now, if you look at the bodies separately, let's do that. See, let's just look at A. We'll just look at A. Here's A. Now, see, A has got that 20 pounds of weight, but it has a 20 pounds normal force. See it? It's got a 20-pound normal force, and it's going to have a frictional force, but we don't know our problem is we don't know whether it's static friction or kinetic friction, but it's one or the other. But don't forget it also has the 50-pound external force is applied to A. So why don't we do Newton's second law? That's what this chapter is. This chapter 13 is Newton's second law. Let's apply that to this body A. Okay. Well, the way to do that is the sum of the forces on your body A is equal to the mass times the acceleration of A. All right. Now here's, you could do the y direction, but the y direction is pretty boring because you got 20 going down and 20 going up. What we want to do is this x direction. Let's have x going over this way. And we're just going to do the x direction. Okay. So what we have is, well, we have 50 minus the friction equals the mass. Now remember, it's got to be in slugs. You have to have the mass in slugs. Now this will be the acceleration of A. I'm not sure about B. We're just doing body A now. Now here's where we're going to think about this. The maximum possible static friction that you can get would be 0.4 times the normal on A, which would be 0.4 times 20. I can do that in my head. Time to show off a little bit. That's 8 pounds, isn't it? That's 8 pounds. So that's the maximum you could get. 8 pounds. Okay, well, maybe that's what you have. I don't know. Maybe it's kinetic friction. See, if it's kinetic friction, it would be 0.3 times the normal, which is 20 pounds. I can do that in my head too. Time to show off again. That would be 6 pounds. Well, I don't know whether it's 6 or 20. I just really don't know. Here's the thing though, if it's static friction, that means that these blocks don't slide. They don't slide if it's static. So you could you could look at the whole thing as staying together and not coming apart. And if you do that, let's do that. Let's write the equation, the Newton's second law. I have room down here. Yeah. Let's write it for the whole thing. Okay. Well, there's the forces. See these frictional forces acting between the bodies cancel out on the whole thing. Because when you do the body B here, if this is static friction going this way on body A, well, then the static friction on body B would be equal and opposite. And on the whole thing, those cancel out and you don't include them. I don't know if that made any sense. But if you do this whole thing, what you got is 50 pounds going to the right. There is no friction down here. It's smooth. And we don't care about the up and down. We just care about the x direction. So you got 50 pounds equal to the mass of the whole thing, which is 70 divided by 32.2 slugs. times the acceleration of the whole thing. Hey, well, we could get that. We could get the acceleration of the whole thing. Well, let's do it. You guys have calculators. Put that in your calculator. If they don't slide together, if they don't slide, come apart and they go together, find the acceleration of the whole thing. Go for it. Well, I got an answer. I got an answer. What did you get? Let me go to one of my excellent students here. Jackson, unmute and tell me, are you with us, Jackson?
Yeah.
Yeah, what'd you come up with?
23.
That's what I got. I got acceleration is 23. Jackson, what would be the units on that 23?
It'd have to be feet per second squared, right?
Good going, feet per second squared. Good going, Jackson. Now, coming back up here, if that's the acceleration of either one of these, I don't see why we couldn't plug it in here because that's the acceleration. It's 23. Jackson came up with it. Well, let's do that and see what that friction is. Put 23 feet per second squared in there and solve for the friction. Go ahead. I'm going to do it. I want you to do it. I got an answer. I got an answer for the friction on the little block, which would equal the friction on the big block. It's just they're equal and opposite. I got 35.7 pounds, and I'm waiting for an uh-huh.
Uh-huh.
Yeah, there you go. Well, now here's the problem, guys. The maximum possible static friction is 20 pounds. Do you understand? Static friction is less than or equal to, no, wait a minute. No, not 20 pounds. 8 pounds, right? Didn't we figure that out? Yeah.
Uh-huh.
Well, gosh, we can't get any 35 pounds of static friction. They're going to come apart. We just figured out they're going to come apart. So you can just forget this right now. It's not going to do that. This block here is it's going to slide, and I can tell you what the friction is now. It's 6 pounds. It's 0.3 times 20, which is 6 pounds. So here, let's put it in here. Look here. This is 6. I'm kind of running out of room here. But see, the friction is 6 pounds. It's kinetic friction. Okay, now we can figure out the acceleration of the blocks. I just need some room here someplace. Did you understand all that? I'm hoping you did. There's a little room in here. Let me shove it in here someplace. Now I want you to look at this diagram here. We know all the forces on it, so we can get the acceleration. Here we go. The sum of the forces on this little block A is 50 going to the right minus 6 going to the left. See, that's kinetic friction. It's 0.3 times 20, which is 6 pounds, equals the mass, which is, it's got to be in slugs. Now this is going to be the acceleration of A. And we're going to solve that. You go ahead. Can you all read my writing? Yeah, you can read my writing. Yeah. Find the acceleration of the little block. Go for it. I got the acceleration of the little block is 70.84 feet per second squared. And I'm waiting for an
Yep, I got it.
Yay, good going. Now we're going to do the big block. Now to do this, you got to draw the diagram. Well, I kind of got started on it here, but let me finish drawing it. We know that we have a weight of 50 pounds. We have a weight of 50 pounds. And we have a normal of 70 pounds. Does that show up? Yeah, that shows up pretty good. We have a normal of 70 pounds, pushing up on the big block. A weight of 50 pounds. And we also have a normal of 20 pounds. See, there's a normal of 20 pounds on the little block going up, but there's an equal and opposite reaction of 20-pound normal going down. Well, you got 70 going down, 70 going up. But see, you have a kinetic frictional force of 6 pounds going to the right. You don't have this 50 pounds. That's on body A. On body B, all you have is that 6 pounds. I think I'm done. If that shows up and you can read it there, yeah, that's it. That's the free body diagram for body A. And now we can write our Newton's second law. Here goes. Sum of the forces in the x direction on body A equals, no, I'm getting mixed up. This is body B. We're doing body B. Okay, well, all you got is a 6 pounds. And the mass is 50 divided by 32.2 slugs. Hey, we can get the acceleration of B. Put it in your calculators. Let's get the acceleration of B. Well, I got an answer, guys. I'm getting the acceleration of B isn't very much. 3.864, but it is accelerating. It's accelerating to the right.
Don't you take into account the friction on the bottom too?
It's smooth. Down here, it's smooth.
So that means there's no friction.
That means there's no friction.
Okay.
Now who am I talking to?
Nicholas.
Hey, thank you, Nicholas. No, there's no friction, Nicholas, on the bottom. They said it was smooth. Okay, well, let's see how we did. This is a review problem. We just did review problem 13.3, and Nicholas had an intelligent question there, but there is no friction on the bottom. But now, here we go. Review 13.3. I found it. It's in the back. It says acceleration of B is 3.86. The book says acceleration of B is 3.86. I'm pretty happy with that. Feet per second squared. Yay, we got that. And then the book said the acceleration of A is 70.8. The book says acceleration of A is 70.8 feet per second. Hey, we did good. We used Newton's second law on that, didn't we? Plus, we got to experience a little stuff about static versus kinetic friction. Any comments or questions on that problem? Okay, I guess you're happy with it then. All right, nobody said anything. All right, well, we're going to do another one of these review problems to finish up our study of chapter 13, Newton's second law. This chapter is the most important chapter in the book, Newton's second law. If we can just master that, we'll be doing okay. So let me erase this. We'll do another one of these Newton's second law problems now. There's a thank you point right there. I forget who got it, and I forgot why. But you know who it is, and I'm proud of you. All right, now this one's a review problem 13.7. Review problem 13.7. I don't know if that shows up on your board or not. There's a little black strip that says Talking Vince Griffin there. I don't want that on there. I'm trying to get rid of it, but it won't go away. Oh, well, we'll just have to live with it, I guess. Okay, now help me find it. This is on page 177. And they have a 10-pound, oh, it's English again. We're practicing English. That's good. We need to know how to do English. 10-pound suitcase slides down a curved ramp. Well, it's not a circle, though. It's kind of a parabola. You guys all know how parabolas go. They kind of go like that. And then if you continued it, it would go like that. Only this one doesn't, it quits being a parabola and it just goes straight for a while. And they've got a block there, somewhere right in here. Here's your y-axis. Here's your x-axis. And this distance, they said, is 6 feet. You're going to come over here, 6 feet. Now this has an equation, y equals 1/8 x squared. 10 pound. It's a 10-pound suitcase. I guess it's kind of like at the airport, you know, when you get your suitcase that comes sliding sliding down this carousel and you stand there and you keep looking for your suitcase. Now we're going to need the radius of curvature. You know what that is. Here, I'll draw it for you. I'll put it in green. Somewhere out here is this thing called the radius of curvature. It's a Greek letter rho, R-H-O. And there's a nice formula for it. It goes, it's in the flap of your book. We've done it before. But to do this, and what they did was this value of x is really -6. But I guess when you square -6, you get a +36. We're going to need dy dx. And I think that's going to be 2/8 times x, which is x/4. Now, if I get something wrong, you speak up. But I think that's the first derivative with respect to x, right? Yeah, I think that's right. Now let's do the second derivative. Maybe I should. We'll do it down here. Second derivative with respect to x is, well, that'd just be 1/4, wouldn't it? Yeah, we can handle that. Okay, I'm going to shut up for just a tiny minute here, and I want you to find the radius of curvature. Go ahead, and I'll call on one of you. We're going to get the radius of curvature. Go. Now keep in mind that x is really -6. See it? I mean, here's x, and you're over here -6. Okay. Let me go to one of my wonderful students here. Taylor, unmute and say hello. Taylor.
Hello.
Taylor, have you figured out the radius of curvature of this curve right here where that box is?
I came up with an answer, and that answer is 23.436 feet.
Taylor, you might be right, and I might be wrong. That's not what I got. Let me do mine again. Just hold on. Taylor, what did you get again?
23.4?
Yeah, you're right. I did it wrong. Good for you. I'm coming up with 23. Doesn't that make you feel good when you're smarter than your instructor, Taylor? It should make you feel pretty good.
I just got lucky.
I'm getting 23 point, I don't know, round it off to 44 feet. How's that? Okay. Does that look right? Well, see, if that's 6 feet, this radius of curvature is a lot bigger than that. I mean, that's 6 feet. Here, let me kind of fake this. Let's see. There's 6, there's 12. 18. You know what? That radius of curvature is way the heck out there like that. But see, it's not curved that much right there, is it? It's kind of flat, really. No, I think it's right. I think we did a good job. Okay, so what? Well, we got to do Newton's second law, I bet. Let me read this. Let's see. Oh, it's got a kinetic coefficient of friction. Let me write that down. Mu sub k is equal to 0.2. When at point A, it has a speed of 5 feet per second. Here, let me do that. It's got a speed of 5 feet per second. 5 feet per second. Good. Okay, now what we're going to do is, whenever you do these problems, if you want to do them right, you're going to have to draw the forces in red. And I do my unit vectors in green, but you don't have to do yours in green. But you have to do them somehow. We're going to pause for a tiny minute. And what I want you to do is scribble down on your paper there. Grab a piece of paper, and I want you to put your forces in red. Does that show up red? Well, kind of, yeah. I want your forces in red. This is how we do our problems. And then we put our unit vectors. Now, in this case here, we want a unit vector in the tangential direction and a unit vector in the normal direction. I'm going to shut up here for a minute. And on your sheet of paper there, on your notebook or whatever, just scribble down a thing like this and then put the forces in red. Well, if you have a red, put the forces on your block and then put the unit vectors. Go for it. I'll be quiet. You do it. Okay, well, it's time to pick on one of my favorite students here. Let's see, I picked on Taylor the last time. Stuart, unmute and say hi, please.
Hello.
Stuart, tell me where I'm supposed to put my tangential unit vector. At the body, what direction is it, Stuart? I need my tangential unit vector. Where do I put it? Stuart.
Is it in the direction the box is traveling?
Yes, that is correct. So here, let's put it right here. There's your tangential unit vector. Now, Stuart, where do I put my normal unit vector?
90 degrees from that.
Yeah. But do I go up or down on it, Stuart?
Up.
Yeah, good going. Good going. There's your normal unit vector. Good going, Stuart. I'll pick on somebody else for the forces. Stuart did a fine job on that. But let me tell you guys, if you get those wrong, you're not going to get your problem right. If you screw up on those, it's over. You're gonna get the wrong answers. Okay, now let me find another wonderful student. Shane, unmute and say hello, please.
Hi.
Hey, Shane, we need some red things. We need some forces on this box. I'm
Yeah.
listening. You tell me what to do here now. What do I do?
I got 10 pounds going down.
Yeah, just a minute. Let me do that. I like that a lot. You got the 10 pounds. That's the weight, and it's going down. What else do I have, Stuart? No, I mean,
Good.
I'm talking to Shane now, right?
Yeah.
Yeah, Shane. What else, Shane?
The normal coming back up.
Yeah, the normal. Now, where is the normal on this box?
Coming straight
Say
on
that
a curve.
again.
At where the curve is. I don't know.
Yeah.
And the radius curvature, I guess.
Yeah, there you go.
Coming
How
up.
about this? Is this what you mean right here?
Yeah.
That's it. Good going, Shane. That's your normal force. Any other forces, or is that it?
The friction going back to the left.
Ah, the friction. He didn't forget the friction. Good going, Shane. Now, which way do I put my friction on this box?
Like up into the curve.
Yeah. He knows. He knows. There's my friction. Now, do we know what this friction is? No. See, we don't know what the friction is. Well,
It's
at
good.
least you got that right. Good going, Shane. Proud of you. Now, here's the thing, guys. If you fell up on those red things, you're never going to get this right. You've got to have those green things and those red things correct, or it's not going to happen. Okay. Now the next step is, see, there's a step-by-step way of doing this stuff. Step number 1, free body diagram. Here, I'll write it out for you. Step number 1, free body diagram. Ta-da! Step number 2. Well, and then you label it. You put, just a minute, my phone's ringing. Let me see what it is. I don't know what it is, so what do? I push green and then red, and maybe they'll leave me alone. We'll see. They'll probably bug me again. Okay, now let's see. Where was I? People won't leave you alone. Now, the next step, there's a step-by-step process. The next step is the green stuff, the unit vectors. You've got to have those. Next step is the forces. I like them in red. Get yourself a red pencil. Put your forces in there. Now there's the next step is the reason what we're studying this chapter. This next step is Newton's second law. Okay, well, let's do that. I need some room here. How about I erase this? We need that 2344. Let me write that down. 2344 feet. Okay, but I need the room. See, there's a step-by-step process. And what's going to happen to you if you don't do the step-by-step process? Well, you're not going to get it full credit for your stuff, even though you probably, some of you know what you're doing. You're not doing what I want. Humor me. Humor me. Do what I tell you. And then you'll be through with me here, what, in a couple of months? And then you'll have somebody else telling you what to do. Okay. Here we go. Newton's second law. Well, in the tangential direction, we're going to write Newton's second law in the tangential direction. Well, where is the tangential? This way. Okay, well, I see that the normal doesn't have any component, but the friction does, only it's negative. But this, you know what? I need the angle. Okay, well, just a minute. They taught me in school many years ago that you can get the angle that this thing is at. What I'm talking about is this angle down here. See, that angle, why don't we call it theta? I bet you've seen this before. The tangent of theta is equal to the first derivative on a graph. I know you've seen that before. And the first derivative was x over 4. And x is minus 6. And it's minus 1.5, right? Yeah. So get your calculator and find out the arctangent of minus 1.5. I'm getting minus 56.31 degrees. If you don't know how to do that, just speak up and I'll go through it more slowly. And what they're talking about is this angle here. This angle here, it's the angle of the hill. This is minus 56.31 degrees. It's the same angle as this angle down here that I drew. You could draw another angle down here. It's the same 56.31 degrees down here. Okay, I needed that angle so I can get my components. Okay, now let me think now. You see that 10 pounds there? There's a 10 pound. Maybe I could draw it here. That might help. Yeah, let me draw it there. Maybe this will help somebody. If this is 10 pounds, see, that has components. There's a component here and a component here. Now this component here is in the tangential direction, isn't it? Isn't it? Yeah, I think it is. And that component will be, it will be 10 pounds times the cosine of this angle, or else you could take it the sine of that angle. That would be fine. It's equal, here, let me write it up here. It's 10 pounds times the sine of 56.31 degrees. Or if you prefer, the cosine of 33.69 comes out the same. See, this angle here is 33.69. You've got to know how to take components of vectors. Okay, well, we got that. What we're doing now is we're taking the sum of the forces in a tangential direction. And what this is the component of the 10 pounds. Then you have to subtract your friction. But now see, the problem is, I don't know what the normal is, but the friction will be 0.2 times the normal. I know that much. And that's it on the left. And on the right, we have your mass. Oh, gee, I'm running out of space here. Times the acceleration. And the thing is, we can get the acceleration. If I had some room, I could get it. Now, let me make some room. Okay, here's what we got. We got the sum of the forces in the tangential direction are 10 pounds sine of 56, 31 minus 0.2 times the normal equals v squared over r. No, the mass. It's equal to the mass in slugs. See, there's your slugs. V squared over r. Well, they gave us the v. It's 5 feet per second. And we cooked up the radius of curvature a long time ago. It's 2344. That's it. Ta-da. Let me box that up. That's a nice little equation. See it? Nice little equation. And so we can get that normal force. Is that what they want? Let me read this. Yeah, find the normal force. We'll do that. We'll find the no, wait a minute. No. This is all wrong. This is all wrong. This is what's wrong about it. Now that was correct what I did there. What goes here is the acceleration in the tangential direction, not the normal direction. If you're doing the tangential direction stuff, everything's got to be tangential. You know what I did? I forgot what I was doing. And I put the normal acceleration in there. Do you understand? If you're doing the tangential stuff, you want the tangential stuff. Okay, there it is. All right. Dang, we don't know what the normal is. Can't solve it. Okay, but we don't give up easy around here. We just write our other equation. Here, let's find it here. Let me make some room. We'll make some room down here. Here we go. Now what we're going to write now is the sum of the Newton's second law. Oh, gee, I just dropped something. Did you ever drop something and then it just disappears out of existence entirely? Yeah, there it is. Okay. All right, we're going to do the sum of the forces in the normal direction now. Now, you have to know where the normal direction is. And one of my excellent students told me it's right there. And so you have this normal, that's in the normal direction. The friction doesn't have a component in the normal. But the 10 pounds does. And you know what it is? It's right here, isn't it? But it's going the wrong way. It's minus 10 pounds. It'd be the cosine of the 56. Or you could say sine of 33, doesn't matter. Sine of 33 is 69. Or you could say cosine of 56 31, that'd be okay. I think that's it. See, that's in the normal, yeah. And that's going against the normal. And this is going to equal your mass in slugs times acceleration and tangential, which is equal to v dot. It's equal to dv dt. If you look in the flap of your book. Nice equation there. Let's box it up. Nice equation there. No, again, I'm getting mixed up. Now, this will happen to you someday. I did it again. What I need here is the normal acceleration, which is v squared over r. So I want to take my v and square it. There you go. And then divide by 23/44. Okay, here's my other equation. Here's my Newton's second law in the normal direction. I've got my normal force. I've got my component in the normal direction of the weight. Yeah, I think that's right. Yeah, I think that's right. It equals the mass in slugs times the acceleration in the normal direction, v squared over r. That's it. Hey, look at here. We can get our normal, we can solve this and get our normal force. And then once you know the normal force, you can plug it in here and get your tangential acceleration. I'm going to shut up now for a couple of minutes. I want you to solve for those. And I'm going to do the same. Go for it. I don't know if this is right, but so far here's what I'm coming up with. Could be wrong, but we'll see. Anybody getting what I'm getting?
Yes, sir.
That makes me feel good. Anybody else?
That's what I got.
I bet it's right if there's three of us. Let's look in the back and see what they said. This was review problem 13.7. And it says the normal force is 5.88. Yay, we did great. They said it's 5.88 in the book. And round ours off, we got what they got. And they said the tangential acceleration is 23.0. How about that? Feet per second squared. Okay, is there anything about that problem that's bugging anybody that you need me to try to explain? Well, okay, if you think you're happy with that. Any last comments on that? Okay, and you know the drill. You make the free body diagram, you do something with green stuff, you do something with red stuff, you write your N2L. That's how you do these problems. Okay, well, let's go into the exciting chapter 14, and let me hit some highlights and work a problem. That sounds like fun to me. They have at the beginning of chapter 14. I'm going to hit some highlights and then we'll work a problem. Chapter 14 is about energy. They start off and talk to you about work. Well, work is force times distance. They use a U for work. I don't like that. I like W for work. And what it is, it's just the force. It's really a dot product of force times the distance. They use different symbols, but it means the same thing. And they have the work done by springs. I don't know if you remember Hooke's law. Here's some highlights of our chapter. Hooke's law says the force of a spring, we'll put a little S there for a spring, it's actually negative kx. If you pull on a spring, it always pulls back the opposite direction. If you compress a spring, it always pushes back in the opposite direction. That's what the minus is for. See, this is the actual force of the spring. The force of an external agent that is causing the spring to compress or expand, if you talk about the force of an external agent, an outside force, it's a plus kx. This is in your book. It happens to be on page 182. See, if you have a spring and you stretch it, you connect this one to a solid wall or something there, and if you have an external force that's doing this, see, that's an external force. Guess what the spring does? When you pull a spring that way, it pulls back that way. The force of the spring, that's where the minus comes from. But the amount is k times x, where k is called the spring constant. K is in units of newtons per meter, or it could be in pounds per inch or pounds per foot. The most important equation in this chapter is what they call the principle of work and energy. So we talked about the definition of work. We talked about, I didn't do the work of a spring though. Time out, and let me do that for you. We'll get the work of a spring here. If you want the work of a spring, well, see, that would be the integral of minus kx dx. This is just a dummy variable. And so if you stretched a spring and you integrated this from 0 to some distance, I don't know, some length or whatever, some value of x maybe. You guys all know how to integrate that. You get a minus k x squared over 2. And you're done. That's it. The work of the spring is negative because remember you're stretching it, but the spring is pulling back, and when the force is a force that's opposite to your motion gives you negative work. The work done by the external agent is a positive kx squared over 2. Okay, good. Enough on that, and let's talk about the next important item, the most important item in our chapter, and that's what they call the principle of work and energy. The principle of work and energy, that's what they call it. Most books call it the work energy theorem. The work energy equation. It goes by a different name. I like the work energy theorem. And it goes like this. If you add up all the works done on a body, it's equal to the change in kinetic energy of the body. If you're lazy like me, you just write this as delta KE. Take your final kinetic energy, subtract your initial kinetic energy. This is the total of all the work done on the body. Now they prove that theorem on page 184. I bet you've had it in Physics 1 and maybe in other classes. I don't think I'm going to take the time. I'd like to do a problem. We only have 15 minutes is a sad thing. I'm not going to take the time and prove it to you right now. I'd like to. Maybe we can. But they don't write it like that. They write it goofy. They go like this. But it means the same thing. This may not look like this, but it's the same thing. Their secret symbol T is kinetic energy, and that secret symbol of U there, that's their symbol for work. I don't know why they have to make it so goofy looking. The other important equation in this chapter is on page I can never find anything. There it is. On page 215 is the definition of potential energy. Now, the way I would write this equation is the change in potential energy is equal to the negative of the work done by what they call a conservative force. What it is, it's a force that creates potential energy, like gravity. There's gravitational potential energy. Actually, in this chapter, there's only two kinds of potential energy. There's gravitational potential energy, and there is elastic potential energy. Those are the only two kinds that we know about. There are others. There are other kinds of potential energy, but these are the only two in this chapter. But the way they write this equation is they don't write it like this. They write it like this. They just want to confuse you, I guess. They don't want too many engineers out there. But it means the same thing. This is the work done going from one condition to another. And this is their secret symbol for potential energy. Now they have initial minus final, which is the negative of final minus initial. It amounts to the same thing. So you put the minus on that side, and this is their symbol for work. This, in fact, is a definition of what potential energy is. And all you have to know about is that these two kinds. Now, gravitational potential energy is mgh, and elastic potential energy is 1/2 kx squared. We just talked about that. Okay, enough theory. Let's work a problem. Do we have time? We have 11 minutes. You can do a lot in 11 minutes. So we're going to try to work a problem. Let me find one that I like here that maybe we can do in 11 minutes. Okay, now this is problem F14.3. It's a fundamental problem. They have answers in the back. I'm going to erase all this so I'll have plenty of room. And I'm going to draw this thing. They've got this building here. And the distance up above the ground of this block here is called S. And the block is connected to a pulley. Yeah. Let's see if I can do this right. The block is connected to a pulley. Yeah. This goes way the heck up here. And this pulley okay, yeah, here we go. Comes over here and there's this block. No, it's not a block. Sorry about that. It's a motor. Okay, and now what about this pulley here? Well, this comes up, getting confused now. I'm doing okay. Yeah. Well, we have to connect this pulley to something so it doesn't fall. And we're just going to come up here, tie that to that. That'll be fine. Yeah. Okay, good. And don't really like the way that is, but I think that'll work. Now let's read the problem. This is F14.3. The motor exerts a force equal to 600 plus 2s squared, where CS is the distance of the body down there. How much does it weigh? Did they tell us? 100 kilograms. This is 100 kilograms. All right, pretty heavy, around 220 pounds. Pretty heavy crate there. And it says here, it's going to go up 15 feet. It's going to go up 15 feet. See, as this motor pulls in this this cord, this pulley will go up. It'll go up. It'll go up. It'll go up, and it's going to go up. It's going to make this box go up 15 feet. Okay, no, meters. The box is going to go up 15 meters. It's initially at rest. Okay. We want to find the speed of the box when it has risen to 15 meters. See, that'll be up here someplace. I don't know how far, maybe this far up, you think? See, the box will be here now. And the whole thing will be up here someplace. Yeah, there you go. Because this motor is pulling that rope in there. Okay, well, that's the force. How am I doing on time? I got 5 minutes. I better figure this out. We're going to use this equation here. It's called the work energy theorem. If we can figure out the total work done on the crate, now you understand this is the force that the motor has on it. I don't know, you could call that tension if you wanted to. That's the tension. Put a T there. That's the tension that the motor has. Of course, it varies with where it is. But see that you have tension here and you have tension there. But see, the work done on the crate is you got 2 tensions times your force. Now, you can't just go 2T times 15 meters. It's going to go up 15 meters. But the total work is not 2T times 15 meters because the tension is changing. It's 2T, but the tension itself is changing. To get the work done on the crate, you're going to have to go and integrate 2T times the distance it travels. See, that's why they invented calculus. In case something is changing on you, you can't use a constant. It's not a constant. The tension's getting bigger. Okay, but we can do it. It's going to be 600. And now keep in mind, now this is just the work done by the motor. The work done by the motor is 600 plus 2s squared ds from 0 to 15. What do you think? Yeah. Oh, no, wait a minute. Oh, I need a 2 in front of the whole thing. Just a second. I need a 2 in front of the whole thing. There you go. That's the work done by the motor. Now that's not the total work, because see, gravity's doing some work too. Now let me write that. The work done by gravity, it's going to be negative. It's 981 newtons times 15 meters. Does that make sense? See, it is constant. Gravity is a constant 981 newtons, right? You know. Hey, wait a minute. I didn't put my red markers on there. Here we go. There's your 2t, and there's your 981 newtons. Yeah. That 2t is going to be bigger than that. Probably ought to make it bigger. There you go. How am I doing on time? Oh, gee. I only have 2 minutes left. Okay, well, here, let me write it out, and you guys can finish this. The total work done is going to be the work of the motor, which is from 0 to 15 meters, 2 times the 600 plus 2s ds, yeah, minus, you're going to have to subtract the work done by gravity to get the total work done. Okay, need a little room here. Minus.
Is it a 2s squared?
Absolutely. Another
Surplus
thank you.
stuff.
Another thank you point goes right up there in the corner. Proud of you. I forgot my square, but it's okay now, I think. Minus. Now I know this is work is negative, but we're taking the sum of the works. That means you add them all up, and when you add this, it's a negative 981 newtons times 15 meters equals equals the final kinetic energy, which is 1/2 mv squared minus the initial. It started at rest. Guys, if I had time, I know we could do this, because I know you can integrate that, subtract that, that'll give you the total work done. And that's going to be turns out to be the final kinetic energy, and you can get your answer in the back, and they show you how to do it in the back. So finish that off just for pure enjoyment. But we're going to have to say goodbye for now. Here's your last chance to say anything. We're going to say goodbye. Nobody said anything. Goodbye, students. I'll see you Wednesday at 9:30. Adios, muchachos. Take care.